taking a look at section 14.5, we're now going to talk about the chain rule. So the chain rule, really confusing when you look at the notation behind it, right? This all is like, wait, what does all of that mean? It's actually pretty simple in application. The idea here is if you have z as some function of x and y are both functions of other variables, and you want to take the derivative of z with respect to t, for example, then you can't go right from z to t because z is not a function of t, z is a function of x and y. So you have to go from z to x or y, and then from x or y to your t's. We'll make sense out of all that. Tree diagrams, super important. I know most instructors use tree diagrams to teach this. Some instructors don't. And those instructors, I just have no idea how the fuck they're teaching this because I literally cannot do these without drawing a tree diagram. What do I mean? Let's take a look at an example. All right, this says find dz dt for this function right here, where z is a function of x and y, x is a function of s and t, and y is a function of s and t. Okay, so let's go ahead and draw out a tree diagram. So we have z, that's kind of our starting point. And z is a function of what? Z is a function of x and y. So we'll break that into our x and y branches. Now x is a function of s and t, and y is also a function of s and t. Now, what am I trying to find overall? I'm trying to find dz dt. So what I'm going to do is I'm going to look at my tree diagram, and I'm going to choose all of the paths that I can take to get from z to t. So I can go from z to x and then x to t. That's one path that I can choose. I could also go from z to y and then y to t. So I have two different paths that I can choose to get from z to t, and I need to take into account both of those paths when I'm writing out my formula for dz dt. So what do I mean? dz dt equals. So the first way I can get from z to t is to go z to x, x to t. So my first part of the formula would be dz dx times dx dt. Okay, and you can see, by the way, if you have dz dx times dx dt, what would happen here? The dx's would cancel out if you multiplied them together, and you would just be left with dz dt. So that's the idea here. That's the whole idea behind this chain rule. But since z is a function of not just x, x and y, we can't just do this to the x's. We also have to do that to the y's. So it'd be plus dz dy times dy dt. Now, the way that I like to approach this, and I'm going to make myself disappear because this is a long problem, is I like to kind of find all my partial derivatives first and then plug back into this formula. So I kind of like to sidebar, find everything that I need, and then plug back in. So I'm going to start by finding dz dx. I'm just going to kind of come down here to do that. So if I find dz dx, I want to look at my z function and take its derivative with respect to x. To do that, we're going to need a product rule. So it'd be root x left alone times the derivative of e to the xy, which would be y e to the xy, plus e to the xy left alone times the derivative of square root of x, which would be 1 over 2 root x. Okay. Now I'm going to find my dx dt. To find my dx dt, I'm going to look at my x and take the derivative with respect to t. So that would just be 2s. Now I'm going to find my dz dy. So looking back up at my z, if I take that partial derivative with respect to y, now that root x is just a number, and then the derivative of e to the xy is going to be x e to the xy. And then our dy dt, we would take a look at our y's and take the derivative with respect to t. So that 4s squared is all just a number, so the derivative of negative t squared would be negative 2t. Now, what I want to do is I want to evaluate these when s is 1 and t is 2. So let's talk about what that would look like. When s is 1 and t is 2, In order to find all of these different things we need to know, yes, sometimes we plug in S's and T's, but we also need to know what our X and Y values are there, what our X and Y values are there. So I'm going to take my X and I'm going to say, okay, when S is 1 and T is 2, X is going to be 2 times 1 times 2, which would give me 4. And my Y would be 4 times 1 squared minus 2 squared, which would give me 0. Okay, so I know overall that S is 1, T is 2, X is 4, and Y is 0. And I can use each of these values to plug into all of those partial derivatives. So plugging in here, if I plug in a 4 for X and a 0 for Y, that whole term is going to go to 0. E to the 0 is 1. And then plugging in a 4 for X, that would give us 2 times 2, so that would give us 1/4 right there. Plugging in a 1 for S, that's going to give us 2 times 1, which is 2. Coming over here, plugging in a 4 for our X, that's going to be 2 times 4 times e to the 0, which is just 1, so that gives us 8. And then right here, negative 2 times the t value of 2, that gives us a negative 4. Okay, so now that I have all of these values, I can go back up to my original formula right here. And plug everything in. So dz dt equals our dz dx, which was 1/4, times our dx dt, which is 2, plus our dz dy, which is 8, times our dy dt, which is negative 4. So overall, 1/4 times 2 would be 1/2. 1/2 minus 32. That would be 1/2 minus 64 over 2. So 1 minus 64 would give us negative 63 over 2. Answer. All right, we're going to do a couple more examples. And if you feel like you got the hang of this and you're like, I got this, I don't need to watch the rest of this section, I know chain rule, I would encourage you to make sure that you don't skip over the very last example where we get into implicit. However, if you feel like you got the hang of this and you want to try this one here on your own, go ahead, try to pause the video, work this one through on your own and see if you can do that. I'm going to work through it up here because this one has 3 independent variables to start with, not 2, so it does get a little bit more complicated, but let's go ahead and work through it. Here, overall, we're looking for dr du, and we start with our r, which is a function of x's, y's, and z's. And x is a function of u and v, y is a function of u and v, and z is a function of u and v. Does anyone else feel like their u's and v's always look the same? No, just me? Okay. All right, so we're going to go r to x. What are we trying to do overall? Dr du. So we're going to go r to x, x to u. That's one way to get to u. R to y, y to u. R to z, z to u. So there's 3 paths to get from z to u. So we're going to be adding 3 things together in our formula here. Let's go ahead and write this formula down. So our dr du is going to be equal to dr dx times dx du plus, then we're going to go dr dy times dy du, and then dr dz times dz du. And just like last time, I'm going to go ahead and find all my partial derivatives first and then plug into my big formula overall. It just helps me organize the problem a little bit better when I do it that way. So start with dr dx. So dr dx, if you want to take the derivative of r with respect to x, overall in our r, we have the natural log of something. So it's going to be 1 over that thing. So 1 over 2x plus 3y squared plus e to the z. and then times the derivative of the inside with respect to x, so times 2. So that becomes a 2 on top. Then we're going to do our dx du. So our dx du would be 6u. Then we're going to do our dr dy. So our dr dy would be, no, sorry. Yeah, our dr dy would be this guy, his derivative with respect to y. So it would be 1 over this inside function times the derivative of 3y squared, which is 6y. Then we're going to do our dy du. So when we do our dy du, that's going to be the derivative of y with respect to u, which is v over 2. Then our dr dz. So that would be our 1 over this term here times the derivative with respect to z, which would just be e to the z, and then our dz du. Are these labor intensive? Yes, but they're not that difficult. All right, so those are all of our partial derivatives. Now we know that u is 1 and v is 2. So we're going to find out what our x, y, and z are as a result. When our u is 1 and our v is 2, our x is going to be 3 times 1 squared minus 2 squared. So that's going to be 3 minus 4, which is negative 1. Then our y is going to be u times v, so 1 times 2 divided by 2, which is positive 1. And then our z is going to be v, which is 2 minus 2 times 1, which would be 0. All right, so we have u is 1, v is 2, x is negative 1, y is positive 1, and z is 0. All right, I just like having all of my values that I'm plugging in one place. That's why I do that. All right, so plugging all those values in here. That's going to give us a 2 on top. And on bottom, we're going to do 2 times x, so 2 times negative 1, which is negative 2, plus 3 times our y squared, so 3 times 1 squared would be 3. And then on bottom, we have an e to the 0, which is 1. So overall, this entire denominator, which is going to show up a lot, is going to be negative 2 plus 3, which is 1, 1 plus 1, which is 2. So 2 over 2 ends up giving us 1. Here, 6 times our u, which is 1, is going to give us 6. Here, it's going to be 6 times y, so it's going to be a 6 on top, and we already know this bottom simplifies down to 2, so it's going to give us a 3 overall. Here we have 2 over 2, which is 1. Here we have e to the 0, which is 1 over 2. And then here we have just negative 2. There's nothing to plug into there. So we'll take all of these values and come back to our main formula. And that's going to give us that dr du equals our dr dx, which is 1, times dx du, which is 6, plus 3 times 1, plus 1/2 times negative 2. So overall, that gives us 6 plus 3 minus 1. So that gives us an 8 overall. Okay, so now we're going to take a look at the second application of the chain rule. This is the part where students kind of forget to study this sometimes, so don't forget about this application of the chain rule. We're going to use this when you have an implicitly defined function. What does that mean? Well, in the last couple problems, it was r equals some function of x, y, and z, and we wanted to find dr d something. So we had r equals to start with. Here we had z equals to start with, and we wanted to find dz d something. Those are explicitly defined functions. In the next example I'm going to show you, we're going to have something where our z's are going to be kind of jumbled together with our x's and our y's. So instead of z equals, it's x, y's, and z's all jumbled together. That's going to change how you take your chain rule derivative. So in this situation, you're going to want to use these formulas here, which I know look a little confusing. We'll make some sense out of this. The question is, in these formulas, what is this capital F? And this capital F is the function that you get when you take your implicitly defined function and you get everything over to one side of the equation and put a 0 on the other side. So for example, if you have this guy here, notice we have this function here where all of our x, y's, and z's are jumbled together on one side of the equation, and it wants us to compute dz dx and dz dy at a given point. So we can't treat this like a normal partial derivative. We can't solve for z. As much as you want to try here, there's no way to get this as z equals some function of x and y, so we can't take our partial derivative that way, so we have to use the implicit application of the chain rule, and that means the first thing we need to do is find what our f is. So our big F of x, y, z is the function that we get when we take this whole thing and we get everything over to one side. So our f of x, y, z is going to be x squared y plus xz plus yz e to the z. So that, minus 1. Turns out that wouldn't have mattered, but technically that's our f of x, y, z. Okay, so now if you want to find dz dx, the way we're going to find dz dx is, and I find it easier to just kind of know how to apply the formula than to memorize it. When you're trying to find an implicit derivative, it's going to start with negative, and then you're going to go f with respect to whatever variable's on bottom over f of respect to whatever variable's on top. Okay, and over here, if I wanted to find dz dy, we're going to go negative f of our bottom variable, which is y, over f of our top variable, which is z. So just like before, I'm going to compute my partials down below, and then I'll go back and plug them in. So if we want to take the partial with respect to x of this function here, then the derivative of x squared, that would be 2x. The y comes along for the ride. The partial with respect to x here would just be z, and then no more x's, so we're done. Our fy would just be x squared plus z e to the z. And our fz is going to be slightly more complicated. Our fz, that doesn't have anything, that's going to be x. Plus here we need to use a product rule. So when I do the product rule, I'm going to consider the yz as one term and the e to the z as the other. So first left alone, so yz left alone. Derivative of e to the z is e to the z. Plus second left alone times the derivative of the first, the derivative of yz would just be y. Right? And we want to know this at the point 1, 1, 0. So if we plug in a 1 for x and y and a z for 0, that'll give us 2. That will give us 1 plus 0, which would just be 1. And this would give us a 1. That would be 0. That would be 1 times e to the 0, which is 1. So that would be 2. So plugging everything back into our formulas up here, this would be negative. Our fx is 2. Our fz is 2, so this would give me a negative 1 overall. And then over here, this would be negative. Our fy is 1, and our fz is 2, so that would give me a negative 1/2 overall. All right, so that wraps up the chain rule application here, both explicitly and implicitly. Just make sure you're comfortable with both applications because either or both can show up on the exam. That's all for chain rule.